Greetings, math people. In this particular video, we're going to look at understanding AP Calculus sigma notation problems. So let's go ahead and get right into it.
Specialized in science and mathing, original black men, busting thoughts that pierce your mental, the fierce, ripping your section, vocal toe-to-toe, impeccable, splitting your back, son, simple as addition and subtraction, black thought, the infinite relax one.
All right, so just a brief little history. These sigma notation problems in AP Calculus have really only been around since about 2016. That's when they kind of emerged. And they emerged and, they caused some problems. We've stated before, talking about the limit of composite functions, how that caused some problems. And these sigma notation problems cause problems as well. So in this particular video, we're going to teach you everything you need to know to solve these problems. And in fact, you should find them relatively easy. Now, however, we're going to be stressing a conceptual understanding in order to do the problems versus some trick or some little easy rule. So this is not some type of algorithm. This is to be able to do this problem is going to be based on a firm conceptual understanding of what happens as you go from a Riemann sum to a definite integral. So we're going to make sure you have a firm conceptual understanding of that transition, and that will make learning these problems very simple to do. So it's just like the unit circle, for instance. We don't want to work on trying to memorize every single angle. Like I don't want to memorize what the sine of 11 pi over 6 is. I want to, memorize the sine, cosine, and tangent of pi over 4, pi over 6, and pi over 3. But for any other angles, even the quadrantal angles, I want to utilize my understanding of the unit circle in order to figure them out. And so similarly here, we're going to lean heavily on our understanding of the transition from a Riemann sum to a definite integral to be able to figure these problems out. All right. So with that said, let's go ahead and lay the foundation. So I'm going to briefly look at a Riemann sum problem, do a little analysis on that, make sure you understand it. And we've done Riemann sums videos in the past, which we'll put a link up there for. But it's appropriate for this particular video to still do the Riemann sum outline and then go in how it plays into the sigma notation problems that you'll see in AP Calculus. All right, so I'm going to define some function f of x, and I'm going to define it as 18 minus x squared. And what I want to do is I want to find the area under the curve of this function as x goes from 1 to 4. And I'm going to find this area using equally spaced rectangles, and I'm going to use 3 rectangles. So I'm going to use 3 rectangles of equal length, and I'm going to use the right endpoint of each rectangle to actually hit the function. And so this is referred to as a right Riemann sum. And these rectangles can also be referred to as subintervals. So let's go ahead and, outline this scenario and how it looks. So there's our Cartesian plane. And the graph of this particular function, so let's say I graph it in a different color. So the graph of this particular function is a downward facing parabola that has a y-intercept at 18. So we're going to say this is 18 here. It's not going to be up to scale. And, the graph is going to proceed downward like so. And it has an x-intercept at the square root of 18, so a little more than 4. And so 1, 2, 3, 4. So there's 4 there. There's the square root of 18 there. And what we're trying to do is we want to find the area under this curve to the x-axis from 1 to 4. So this is what we're trying to approximate, excuse me. So I'm not going to be able to find the actual area. And I went a little past 4 there. So that the actual area on this curve under this curve from 1 to 4 is actually 33. And so this is going to be an approximation that we'll find. And you will see how close it gets to 33. And so what we're doing, we're using equally spaced rectangles. So I have 3 rectangles, and the right endpoint of each rectangle is going to hit our curve. Now, so what would be the width of each rectangle? Now, notice from 1 to 4, there's a difference of 3 units. And I have 3 rectangles which are equally spaced. So then the width of each rectangle should be 1. Now, what I just kind of said, we have a strict definition for it. And that's the width of each rectangle. We like to call that delta x. And delta x is b minus a over n, where a and b are the beginning and starting points of our interval, and n is the number of rectangles or subintervals we're using. So in this case, this would be 4 minus 1 over 3, or 1. So this delta x is the width of each particular rectangle or each particular subinterval. Now, so I have a rectangle of width 1 on the x-plane. So I have one rectangle from 1 to 2. I have another rectangle from 2 to 3. And the last rectangle is from 3 to 4. So of each of those rectangles, the right part of the rectangle is going to hit the curve. So for instance, this rectangle that's on from 1 to 2, the right endpoint, which is at 2, hits the curve, hits the function, and comes down. This next rectangle from 2 to 3, the right endpoint at 3 hits the function and then goes over. And same thing at 4. From 3 to 4, the guy on the right 4 hits the function. And so the area of these rectangles will give us a fairly good approximation of the area total under this curve from 1 to 4. Now, if you notice, there's some missing spots here. So this is going to be an underestimate of the actual area, because we already said the actual area is 33. And we're not going to really discuss the reasons how we got that in this particular video, but just look on video 4, area under the curve and definite integrals. You understand how we get that value. But the area is 33, so this is going to yield us some number which is less than 33. Now, the reason why this is a very effective way of finding, maybe hard to determine areas is because the area of a rectangle is very easy to find. It's just the length times the width. And we can easily, we already know the width of each rectangle, it's 1. And the length or the height of each rectangle, now again, at this interval from 1 to 2, it's hitting the function at 2. So its height for this first one is simply f of 2. And for the second one from 2 to 3, the height is simply f of 3. And this last one, of course, the height is f of 4. So the area, the approximate area based off this right Riemann sum of this region, since they all have the equal width, I can just, multiply all the heights by that width, even though it's one that doesn't mathematically do anything, but I just want to show that my width or my delta x is being multiplied by the sum of all the heights. And then I can write all the heights, which in this case would be f of 2 plus f of 3 plus f of 4. And then if we wanted to quickly do that calculation, so f of 2 would be, f of 2 would be 18 minus 2 squared. And so that's 18 minus 4, that's 14. f of 3 will be 18 minus 3 squared. That's 18 minus 9. That's 9. And f of 4 would be 18 minus 4 squared. That's 18 minus 16. That's 2. And if we add those up, that's 23 plus 2 is 25. So our right Riemann sum using 3 subintervals for the area of this function from 1 to 4 is 25. And so hopefully you understand how we did that. So I want to just make a couple of comments about what we did and try to write it in a different way. Now for this illustration, I'm choosing to do a right Riemann sum. So that's going to be the basis of what I'm doing is going to be based off a right Riemann sum. But I can also do the same thing using a left Riemann sum. And just for the sake of clarity of understanding, I'm going to briefly illustrate how this problem goes with a left Riemann sum, and then I'm going to get to the bigger picture. So let me quickly just revisit the given problem. All right, so just remind you of the function we're using, f of x, 18 minus x squared. We're going to find the area from 1 to 4 using 3 rectangles. In this example, I'll use left endpoints. So just fairly quickly. So that's 18 again. There's a graph, 1, 2, 3, 4, square root of 18. And again, we're trying to go to area from 1 to 4. Now again, I will find my delta x, which would be the same thing. It would be b minus a divided by n. So it will be 1 again. So the width of each rectangle would be 1. Now, what will happen here, since I'm using left endpoints, or doing a left Riemann sum, is for each rectangle, the endpoint on the left is going to hit the function. So the guy on the left hits it, then it comes over. So from 1 to 2 to 1 hits it. From 2 to 1 to 2 hits it, then it comes over. And from 3 to 4 to 3 hits it, then it comes over. And so I think you can clearly see that this one is going to be an overestimate. This is going to give me some number which is greater than 33, 33 being the actual area of it. And if I look, it's very similar to the previous problem because my delta x is the same. But instead of my heights coming from f of 2, f of 3, and f of 4, my heights are going to come from f of 1, f of 2, and f of 3. And so it would be 1 times f of 1 plus f of 2 plus f of 3. And so if we do the math, we've actually already figured these two out, f of 2 and f of 3. And f of 1 would just be, 18 minus 1 squared, that's 17. So that would be 1 times 17 plus f of 2 was 14 plus f of 3 was 9. And this is 31, 9, 40. So the left Riemann sum gave us 40. All right, so just want to do a quick illustration of the left Riemann sum. All right, so now I want to concentrate back on what we did. Really, I'm going to do a juxtaposition of what we did for both Riemann sums in a more simplistic way of looking at it. And then I'm going to kind of write what we did using sigma notation. All right. So I just want to rewrite the problem, but this time I'm going to kind of do it without using the graph per se. So the problem was f of x equals 18 minus x squared. And we're finding the area from 1 on the interval from as x goes from 1 to 4 using 3 rectangles or 3 subintervals. All right. And our delta x, the length of each subinterval or the width of each rectangle, is 1. So what's going to happen on each of these problems? When you get this delta x, what you do, so you have numbers in your subintervals. They start with a. So I'm going to start with a. In this case, a is 1. And I'm going to write numbers as I keep adding delta x until I get to b. So, and you know, delta x is definitely not always going to be 1. It just happens to be 1 in this case. So I'm going to add 1, and then I get 2, add 1 again, then I get 3, add 1 again, then I get 4. So I've gone from 1 to 4. That's from a to b in increments of delta x. Okay, and these 4 numbers outline 3 subintervals. The whole interval is from 1 to 4, but the 3 subintervals are from 1 to 2, 2 to 3, and 3 to 4. Now, these subintervals represent the beginning and ending of each rectangle from the geometric standpoint. And so if I'm doing a right Riemann sum, I'm going to choose the number on the right of each subinterval. So 1 and 2, I'm going to use the 2. 2 and 3, I'm going to use the 3. 3 and 4, I'm going to use the 4. This is what happens on a right Riemann sum. In essence, a simple way of thinking about it, for a right Riemann sum, you're going to evaluate the function for the height at every number in your subinterval except for the first number. And that should make sense because if I'm going right, you know, that first subinterval, the first number is to the left. So I'm going to use the guy to the right. And coincidentally, if I believe I got enough room to fit this in, if I'm doing a left Riemann sum, so let me write the subintervals here. 1, 2, 3, 4. If I'm doing a left Riemann sum, for each subinterval, the endpoint on the left is going to hit the function. So from 1 to 2, it would be 1. 2 to 3, it would be 2. And 3 to 4, it would be 3. So for a left Riemann sum, for my heights, I use every number in the subinterval except for the last number. Now, I want to write this in a different way. So again, what we're doing for the numbers I'm evaluating the function at to get the heights for a right Riemann sum. So I'm going to move my concentration to a right Riemann sum. I start with a, and the first value is actually a plus delta x. That gives me the first value I evaluate the function at to get the height. And then I add another delta x. So the second one is kind of like a plus 2 delta x. Remember, in this case, delta x is 1. So a times 2 delta x, that's 1 plus 2, and it gives me the second guy. And the third guy will be a times 3 delta x, right? So we're going to write this in a more of a shorthand way. So let's kind of talk about what we're doing. So this a represents this Riemann sum. And what we have is we have this delta x. That's the width of each rectangle. And then we're multiplying that by f of x at different values. So first, again, this is based off a right Riemann sum, it'll be f of x, f of a plus delta x. Next, it'll be f of a plus 2 times delta x. Next, it'll be f of a plus 3 times delta x, etc., until I get to f of a plus n times delta x. Now, in the example I use, I was using 3 subintervals, so n was 3, but n need not be 3. N can be more than 3, or it could be less than 3. Now, I want to talk about a shorthand way of writing a sum such as this. This is a sum, so this is a summation. And sigma notation is the way to write a summation. So just if you're unfamiliar with sigma notation, so this is the capital Greek letter sigma. And say the sigma notation as I goes from 1 to n of some number I. What this means, I in AP Calculus, they tend to use a K here instead of I. So when we start doing the problems, you'll see a K there instead of an I. It's just another letter alphabet. It doesn't really change much, but I was, taught with the I, so I tend to use the I. And then I just means integers from 1 on to n. So first iteration, we go when I is 1. And this is a sum. And then we add. And then we go when I is 2. And then we add. And then I is 3. All the way until we get to n. So I'm going to use this convention, if you will, this sigma notation convention to take care of this delta x, this 1 times delta x, 2 times delta x, 3 times delta x, all the way to n times delta x. I'm just going to write delta x times I as I goes from 1 to n to represent that notation. So my area, and I'm going to write it underneath this to kind of illustrate what I'm doing. My area would be delta x times the sum as I goes from 1 to n of f of a plus delta x times I. All right, so that's the actual formula. Let me make it a formula, for a right Riemann sum of n subintervals. Now, what I'm going to do is just move stuff around a little bit. So sigma, so I goes from 1 to n of f of a plus delta xi times delta x. So that's the actual formula, to find a right Riemann sum. And the only difference for a left Riemann sum, because you remember the left Riemann sum, you don't start with a plus delta x, you actually start with a. So the difference for a left Riemann sum, I write it in a different color here, but I just mentioned I'm really not going to use it for the development of my answer because it's easier to think of this in terms of a right Riemann sum. But for a left Riemann sum, the only difference would be, so we would take the sigma as I goes from 1 to n of f of a plus delta x times 1 minus I delta x. So hopefully you can see that. So this is the difference, for instance, when it's 1, when I is 1, this is 1 minus I there. That I may be difficult to see. When I is 1, that would be 0. And so I would just start with a. And then when I is 2, it would be a plus delta x, etc. So that's the difference for a left Riemann sum. All right. So we have this formula, correct? And so this formula represents a Riemann sum. Now, a definite integral is actually the whole area. So let's go back to our initial drawing. So again, this is an approximation of the area under this curve from 1 to 4. Now, the better approximation I can get by using the same method is to use more rectangles. So the more rectangles I use, the closer and closer this gets to the actual real sum, which we know to be 33. So if I use an infinite number of rectangles, I'll get the true area. So how can we use an infinite number of rectangles based off this formula? Simple. All we have to do is take the limit as n goes to infinity. Remember, n is a number of subintervals, or the number of rectangles. So if I take the limit of this as n goes to infinity, that'll give me the true area under the curve. And so this guy, this is the main formula you need to think about when doing these sigma notation problems. And the base understanding, you're going to take the limit as n goes to infinity. That's generally going to be given. The real thing you need to understand is you're going to have a delta x, and you're going to have f of a plus delta xi, which again, they'll use a k. And we'll look at it when we do the problem. So it'll just be a k instead of an I here and here. But you're going to have delta x and f of a plus delta xi. Not a plus f of delta xi, but f of a plus delta xi. And, you know, this delta x need not be in the summation. It need not be in the back. Generally it is. That's why I moved it to the back. But of course it could be in the front. It could be in front of the sigma. So just that basic understanding. So let's now just go ahead and look at some problems and see what's going on here. So we'll look at 3 examples. All right. So the sun is kind of bearing through a little bit here. I apologize for that. Let me put a blank sheet under these so the marker is not showing. All right, and let me try to block out the sun a little bit. All right, so you see the problem. So it's asking which of the following integral expressions is equal to the following limit. Now we have the limit as n goes to infinity, the sum as k goes from 1 to n of 2 plus 3k over n times 3 over n. Now, the first thing I like to do in these problems, if they give me the sigma notation and asking for the definite integral, and I guess I didn't make mention of how this looks as a definite integral. So let me quickly make that statement. I apologize for not making that statement earlier. Let me put a book up to block the sun. I don't want to close the blinds because the sunlight is pretty good, but that glare right on the paper is not good. All right, it's pretty good. Job well done, book. So again, this represents area under the curve of the function f of x from a to b using n subintervals. So how this is represented as a definite integral is this is equal to the integral from a to b of f of x dx. So that's how it looks as a definite integral. And now the things we can get from the definite integral to this, remember this value delta x is b minus a over n. Well, I have a and b here. So whatever I have for this delta x, the denominator is going to be n. So the numerator better be the difference of these two numbers, b minus a. That guy better be the difference of those numbers, b minus a. And the a that's here, well, that guy better be the same a that's here. And of course, this delta xi, which will be delta xk on the problems, again, that delta x better be the same delta x from taking the difference of these two over n. All right, so let's go back to the problem. So the first thing I like to do with these problems, if they give me the sigma notation first, is quickly identify delta x. There's delta x there. So it's 3 over n. So what that tells me is b minus a better be equal to 3. B minus a better be equal to 3. So as I look at my answer choices, all of them, b minus a is equal to 3. All right, cool. Now what I look for, and I like to see both these matching, which they are, but we'll talk about a problem when they aren't matching because they don't have to match. What I look for is a guy here, which generally is A, but it doesn't have to be A, and I'll make some comments about that momentarily. But I like this guy to be A, right? And I'm looking at what the function is as a whole. The function is simply the square root of something. And so if this is A, then the function is simply the square root of x. So if b minus a is 3, and if a indeed is 2, then b better be 5, right? Okay, so I'm looking for 2 to 5. Okay, 2 to 5, 2 to 5. Now, if this 2 was here, so I'm trying to see which of these is right. If there was indeed a 2 being multiplied by the x, then this wouldn't be 3k over n, because that 3 will be multiplied by 2. It would be 6k over n. But the fact that it's 3k over n, meaning that 3 over n is staying the same, delta x, that means there's nothing being multiplied by the delta x, so it's nothing times x. So it's simply this guy. Now, there are multiple ways to represent this, because this doesn't have to be A. So just for illustration purposes, another definite integral that would be equivalent to this expression, of course, on a multiple choice question, only one would actually work. So they wouldn't give both these answers as answer choices. But just to illustrate, another one that could work would be the integral from 0 to 3 of the square root of 2 plus x dx. So hopefully you can see how that works. So again, the first thing I'll identify is my delta x. So again, my b minus a better be 3. Okay, b minus a is 3. Now I have this 2 here, which could be a, but it doesn't have to be a. It could be part of the function itself. So if the function is 2 plus x, then that 2 can come from there. And so this a is 0. And of course, 0 plus 2 still is 2. And so this is another way of writing this particular expression. Right? It's another way of writing it. And even another way this could be expressed. Okay. So again, you always want to start with this delta x. That's the main thing. All right, so this guy is delta x. Cool, so the difference of a and b better be 3. But let's say it was going from 1 to 4. Okay, my delta x is still going to be 3 over n. But I got this 2 here. Well, what if this was 1 plus x dx? So you can see if the function, if f of x is 1 plus x, well, f of a plus x would give us this 2. Because again, remember, this thing starts with f of a plus delta xi. So if f of x is 1 plus x, f of a plus delta xi would be the 1 plus this 1 would give us 2. So there's just a couple of different ways you can look at that particular problem. I hope that didn't become too confusing. All right, let's look at the next problem. So the next problem, they're giving us a definite integral, and they want to see the correct sigma notation. So when they give me this guy, again, the first thing, I really love starting with delta x. So for this problem, delta x would be 7 minus 3 over n, or 4 over n. So when I look here, I better see 4 over n. if I don't see 4 over n, can't be the answer. All right, so I got all these 4 over n's. All right, very good. Now, a is 3. So the function is sine x, but it's going to be sine of a plus delta xi. So it's going to be sine of 3. So look at this one. It's 3 plus sine. Again, it's f of a plus delta xi, or in this case, delta xk, not a plus f of delta xk. So it can't be 3 plus. Come on, guy, get out of here. Look at this one. There's no sign of the 3. I got to have the function at a plus. There's no 3 there, so this guy has to be the answer. And let's look at it. The function is sine. A is 3, so sine of a plus delta xk is 4k over n. 4k over n, and delta x is 4 over n. All right. Now, the deal is when they give you the definite integral, there's really only one real option for the sigma notation. Now, it's when they give you the sigma notation where there's multiple options for the definite integral. But really, when they give you the definite integral, there's really one option for the sigma notation. And I say really because, this is how it's written as a right Riemann sum. It could be written differently as a left Riemann sum. So just keep that in mind. All right, let's look at our last example here. Where did the guy go? So here is our last example. And again, they're giving me the sigma and they want the definite integral. Now, again, I like to identify delta x. There's delta x. So b minus a better be 1. Now, notice that this is not the same as this. Now, delta x isn't changing. So delta xk is simply k over n. It's going to be k over n. So if you have this 7 being multiplied by this k over n, then that means that the 7 is in the function itself. That's what that means. So when these aren't the same, this scalar multiple here, this 7, in this case, is just in the function itself. All right, so let's look for b minus a's that are equal to 1. And so that wouldn't work. That wouldn't work. And this one is the square root of x, and this one is the square root of 7x. And again, since we have this 7 here, we're going to need a 7 in the function itself. All right, and now the sun has shifted a little bit where the book is no longer providing full protection. I think data protection is there. So we're going to stop there, ladies and gentlemen. The hope is, again, that we clarified how to do these sigma notation AP calculus problems. Again, we could have just went straight to the problems and just told you what to do, but we really believe having that conceptual understanding will help tremendously in being able to do these problems. And we'll see you next time.